So this is what our second lecture in a chapter on ideal gas mixtures. Everything, if it's a gas, it's an ideal gas in this chapter. We were able to talk about generic mixtures, and now we're talking about our favorite mixture. It's called moist air, made up of two components. That's the way we analyze it. It's made up of dry air. That's nitrogen and oxygen and some other trace elements, but we just combine that all and call it dry air. And then we have water vapor. And that water vapor in our air behaves as an ideal gas. We talked about dry, saturated, moist air in between. We had three temperatures, very, very familiar. The dry bulb. The wet bulb is the least familiar. You just probably didn't have a lot of experience with it. And then Dewpoint is a hard one, but all of your life you've been dealing with dew, and you've been seeing the effects of it on your soda bottles or beverages when they're cold in the summer. They get that dew on the outside. Maybe you've seen it in windows, maybe in the morning on your car, on your grass, on the roofs, other things, dewing out. So this one's hard as well, but you have a lot of experience with it. Go slow, think through what is exactly this dew point temperature. You cool that moist air mixture until it's saturated air, and if you've cooled it anymore, some of the vapor would condense and dew out. All right. Then we had two humidities. You are very, very familiar with the relative humidity. You're not as familiar with the humidity ratio. But this is a favorite of engineers that work in this field. We deal with humidity ratio. Omega is the symbol. What is the definition of humidity ratio? It's how many kilograms of vapor in the moist air mixture per kilogram of dry air. Notice it's not per kilogram of moist air. I'll repeat that. It's per kilogram of dry air. Sometimes they'll just show it dimensionless because it is kilogram over kilogram. Just cancel the kilograms, and it is truly dimensionless. But it's kilogram of something divided by kilogram of dry air. Let's solve this problem. We have room, and it contains air at this temperature, 29 degrees C. This total pressure of 97 kilopascal. The partial pressure of the water vapor is given, 3.364 kilopascal. Determine the partial pressure of the dry air in that room. How would you do it? Yeah. So the total pressure is the partial pressure of the dry air plus the partial pressure of the water vapor. And so if I'm looking for the partial pressure of the dry air, it's the total minus the partial pressure of the water vapor. The total pressure was 97 kPa, and the partial pressure of the vapor was 3.364 kPa. The difference is 93. 93.646. Sometimes we need to calculate that numerically as sequence of steps through the solution. Let's go to part B. For the same conditions, what is the relative humidity? Is that the phi? Yes. Yeah, that's relative humidity. It's defined as a ratio of mole fractions, so the mole fraction of the vapor in the moist air mixture divided by the mole fraction that would, if it would have been saturated at that same dry bulb temperature. So the current moist air conditions compared to saturated air at that same dry bulb temperature. Well, that's the definition, but we often use it where it's the partial pressure of the vapor in the mixture divided by the maximum partial pressure that would have been if it would have been saturated air. Oh, I know what that is. That's the saturation pressure at that dry bulb temperature. It's Psat. That's what comes out of table A2, our old familiar friend. How did you go from here to here? Well, just take both numerator and denominator and multiply by P. And then the mole fraction times P, oh, that's the partial pressure. And the mole fraction times P, that's the partial pressure. So we often use partial pressures. We often forget that it really is a ratio of mole fractions. That's the definition of relative humidity. All right. So how do I find that this relative humidity is 83.9%? You just say, I get the partial pressure, 3.364 kilopascal, and I need to divide by Psat. What exactly is that again? The saturation pressure at the dry bulb temperature. What's our dry bulb temperature? 29. We look in our table A2 to save you the effort. There are the numbers abstracted. As you come down here, and there it is, so 4.009 kPa. Cancel the units, relative humidity is dimensionless, and you'll end up with the 83.9%. Look good? Good. Dewpoint temperature. Well, okay, part A was easy, part B was a little harder, part C, well, that's even harder, isn't it? What's the dew point temperature for this problem? The equation's a little funny. It says I'm looking to calculate the dew point temperature. The way I find it is I find the saturation pressure at the dew point temperature is equal to the current vapor pressure in the moist air. So it's like I'm looking to find this. Okay. So I look and I say, okay, well, what is my current vapor pressure in the air? It's at 3.364 kilopascal. That was given in our problem statement. And then you just say, well, at what temperature is the saturation pressure equal to 3.364 kilopascal? You wondered why that number was given the 4 significant digits. Very rare that an input in a problem is given the 4 significant digits, but it avoids the interpolation. So I don't need to interpolate. So what is the dew point? 26 degrees C. So the current conditions of that air, it's 29 degrees C. If I cool it and cool it from 29 to 28 to 27, finally, when I get to 26, if I cooled it some more, some of that water vapor would start to condense somewhere. All right. Part D. What is the mass of water vapor if you had a volume of 1 cubic meter? How would I calculate the mass of the water vapor if I was given a volume of 1 cubic meter of the room air? So either multiply by rho of the vapor in the volume of the, or take the volume and divide by the specific volume of the water vapor. And then our old friend, the ideal gas equation, kicks in, and there's many versions. So one version would be the density of the water vapor is equal to pressure of the water vapor, the partial pressure of the water vapor in that moist air mixture, molar mass of the vapor divided by R bar T. Do you recognize that as ideal gas equation? Yeah. And so sometimes some forms you use a lot, and this is one form. So PM divided by R bar T. So for this problem, what is the partial pressure of the water vapor in our mixture? 3.364. Let me not write kilopascal, but I encourage you to write it. I'm running out of room on here. That would just to chase your units, make sure your units are right. And then what about the molar mass of water? Yeah, 18.01 or 18.02, I forget. It's 02? Oh, right, 18.02. And then R bar, 8.314. Units on that are kilopascal meter cubed per kilomole Kelvin. You've used R bar so many years and semesters, it's your old friend. And then the temperature, that's our 29 plus 273. That's our dry bulb temperature in Kelvin. When we do that, we get a value for rho, multiply that value of rho times the volume, which just happens to be 1. So I could tell you what rho is. Rho is equal to 0.0241 kilogram per meter cubed. What is that? Kilogram of vapor per meter cubed of volume, and that volume holds both dry air as well as water vapor. But it's only the kilograms of water vapor in that 1 cubic meter that we have tracked right there. So there you go. So we're left with that many kilograms. Not a lot, is it? Very little moisture. But that little bit of moisture can have a big impact on your comfort, on the breathability of the air. You ever been in air that's very thick, and maybe your grandparents or somebody doesn't have very good lungs, they have a hard time breathing on a hot, humid day? You're not there yet? Maybe you know that though, right? Anyway, and then also it has a big effect on equipment. Little moisture in the air or dryness in the air has a big effect in manufacturing processes and equipment. Okay, so not a lot of water, but there it is. Okay. What is my humidity ratio? Oh, that was our omega, wasn't it? And the equation, we had the rho of the vapor divided by the rho of the dry air. And we worked that out, and we had 0.622, the partial pressure of the vapor divided by the partial pressure of the dry air. Or sometimes the humidity ratio is 0.622 partial pressure vapor divided by total moist air pressure minus the partial pressure of the vapor. So this PV is the same here and here. They're the same in that equation. Either way, it's just different versions, same equation. Okay, so how am I, if I just say, okay, oh, I forgot. Where does this 0.622 come from? Ratio of the molar masses, that's right. The vapor divided by the dry air, 18.02 divided by 28.97 gives you, rounded off to 3 significant digits, 0.622. And a lot of people just forget where it comes from. It's just magic. It's just, there it is. 0.622, let's run with it, let's use it. Okay, 0.622 times the partial pressure of vapor, 3.364, then it's 97 minus 3.364. Actually, we already did that. We could have done this 93.636. The answer for part A. Could have used it. And when you calculate, you get this. Professor, should there be units on this? Your call. You can put kilogram vapor per kilogram dry air, or just leave it off. Both are correct. Okay. That number is not very high, is it? Right. Okay. Take this experiment, this conceptual thought experiment, and hopefully if you understand this page, you're well on your way to understanding moist air and the behavior. So what do? We have 100 kilopascal, 30 degrees C, 84% relative humidity. The air is cooled at constant pressure. Determine the relative humidity, phi, the dew point, temperature, and the humidity ratio, omega. So those three things, as the air is cooled from 30 to 29, then the 28, then the 27, then the 26, and 25. And you'll need data out of our saturation table for water. So there's some data. Well, here are the results summarized in a table. So we start with initial 30 relative humidity. That dew point temperature, hey, we worked that out, didn't we? Or you could work it out as 27 degrees. And this is omega. All right. So as you cool it, maybe I should cover up the answers and then reveal, right? This is, everybody likes to just reveal it. You know, okay, fine. Sorry, I should have covered them up. I just robbed you of some excellent opportunities to learn. So as you cool it a little bit, what happened to the relative humidity? Yeah. Colder air is less capable of holding a lot of humidity. That's kind of the street slang for what's going on. But what you're seeing is this P sat is a strong function of temperature. And as the temperature goes down, the saturation pressure goes down. And then what about the dew point? It's not changing. You're getting closer to the dew point. You used to be at 30 degrees, now you're at 29. You're only 2 degrees away from dew. But the dew point temperature did not change. It's holding steady at 27. And humidity ratio. Well, I cooled the whole mixture. The vapor's colder in the mixture. It has a temperature of 29, and the dry air has a temperature of 29. But nothing is condensed. The ratio of how much vapor to how much dry air is the same. We cool it a little more. What happened to the relative humidity? Went up. Then, no change, no change. Then you finally hit the dew point temperature. So the dry bulb is equal to the dew point. Hey, if I put another column and called it the wet bulb temperature, can you tell me what the wet bulb temperature would be for that condition? 27. This is that special case where all three temperatures are the same. They're the same numeric value when it's saturated air. All right, so omega is right there, but if I cool it anymore, some of that water vapor is going to condense. Omega is going down. Relative humidity is 100%. What does relative humidity do if I cool it to 26? Does it go above 100%? That's what your football coach said right before the football game. Go give it your 110%. Does that make sense to an engineer? No, no. So it's going to stay there. And then what does the dew point do? Well, it's going to stay saturated air. The dew point's coming down, and you dewed some out. The humidity ratio went down. And then if you cool it some more, it stays at 100%. Dew point drops because it's the same as saturated air, and the humidity ratio goes down. How about the wet bulb, though? That goes 26 and 25 as well. Hard concepts, but hopefully you get it down and you'll understand. All right. There was an old problem. People get confused about humidity. And so some in a building for a number of years it was run this way. It may be an old war story that gets retold too many times and then it loses all relationship to the truth of where it started. But this is the story. So they wanted to dehumidify the air in the building. Right? And so they thought, and it's run on a campus where there's a lot of air conditioning. So what they did was they took it in and they put it in a heater section, heated it up. The heater section, right? And so what happens when it gets really hot? What changes? Phi went down, relative humidity went way down. See? We dehumidified it. We heated it up. And the relative humidity went way down. And then they said, well, it's in the middle of August. I need to now introduce this nice dry air into the room. I need to cool it. Okay, fine. So they put another coil right here with cold water, and they chilled it or cooled it. So the temperature dropped back down. And they thought that was dehumidifying. Do you think that's dehumidifying? Nope. No. Not at all. So they were fooled. They thought this heating was dehumidifying. It was not dehumidifying. The omega was staying the same. The humidity ratio was staying the same. Now, if they really cooled it, they may put a drip pan right under this cooling coil, and they may get some condensate off of it right there. But this was just complete waste of energy. Complete waste of energy. All right, let's press forward. Here's a problem. You have moist air at 40 degrees C, 100 kilopascal, 70, 5% relative humidity. It's in a size, rigid, closed tank, has a volume of 2.5 meter cubed. The contents of the tank are cooled. Determine the heat transfer in kilojoules if the final temperature of the tank is 35. It'll take about 10 kilojoules to cool it. What was the delta T? Well, you went from 40 down to 35. There's a 5 degrees C cooling. That's how much temperature change there is. So you write your first law for the contents of the tank, and it would be something like So the final internal energy minus the initial internal energy of my mixture is equal to the heat transfer coming into the system during the process from initial state 1 to final state 2 minus the work going out of the system from initial state 1 to final state 2. Is there any boundary work? Is there any paddle wheel? Is there any electric power work coming in or out? No. So the works are all 0. And because we are interested in the heat transfer and we know the direction of the heat transfer, that this is really going to be out, I'm going to switch the signs here. And so Q1 to 2 will be cap U1 minus cap U2. And that's going to be out of the system. I'm talking about a positive heat transfer out. This 10 kilojoules didn't heat it up, it cooled it down. Okay. Somebody says, well, I have a mixture. It's called moist air. So let's do this. We'll say, what is the change for the dry air? And then we'll add to the water vapor. That makes sense. So we have to get the mass of the dry air, and then U1 minus U2, the lowercase u's indicating specific internal energy change. And then the mass of the vapor, leave the subscript off because I have it out there. And then U1 minus U2. Hopefully that equation makes sense. Right? All right. So we have a lot of work to get the mass of the dry air. But we've done that, haven't we? Isn't the mass of the dry air equal to the density of the dry air times the volume in the tank? And the density of the dry air, is that the partial pressure of the dry air times the molar mass of the dry air divided by R bar T? Yeah, we just did that. So a little bit of work, but you get both the mass of the vapor, rho of the vapor times the volume. The rho of the vapor is equal to the partial pressure of the vapor, molar mass of the vapor divided by R bar T. The same type of calculations. Both the dry air and the vapor behave as ideal gases. So doable, doable. Okay. What about this change in internal energy of the dry air? Two ways you can go. Use air tables. Most sophisticated, most accurate, going to account for variable specific heats. But look at it's a 5 degrees C temperature change. It's kind of overkill. But go ahead, you can do it. And you're probably going to have to interpolate. Or instead of using variable specific heats in the air table, what's the other strategy? Constant specific heats. And so wouldn't that just be an appropriate C sub V times the initial minus the final temperature? Sure. And so where do you get the specific heat? Constant volume for air? Out of another table, or maybe you have it memorized. It's about 0.71, what, I can't remember, right? If you want to get more accurate, you just say, well, I'm going to evaluate it at 37.5 degrees C, the average temperature for the process. It starts at 40, ends at 35, average temperature. Add 273, find that in Kelvin, go into the table, maybe do a little interpolation, but you just get one CV value. The CV value for dry air. Okay. What about the internal energy of the water vapor, U1 and U2? How do I get that? Professor, you did such a great job of talking. Why don't you continue? Well, it behaves as an ideal gas, and this is going to be U sub G at state 1, and this is going to be U sub G at state 2. What do you mean, U sub G? Isn't G our symbol for vapor, saturated vapor? Yeah. And so we pull that out of our tables, our table A2. Okay, so once you do that, you can find that the answer gives us about 9.44 kilojoules of heat cooling need to be pulled out of the dry air component of that mixture. And 0.64 kilojoules need to be pulled out of the water vapor. There's a lot less water vapor there. And then the total, you just add that up, and so Q1 to 2 out is a positive 10.1 kilojoules of cooling to achieve that. This is about 94% of the percentage of cooling, and this is about 6%. Yes?
So I could use specific heat for the water?
You can, but you've got to get the specific heat constant volume for the water vapor. That's another way of doing it. You definitely can. Yeah, you could have used appropriate C sub B for the vapor, and then T1 minus T2. Yes? Anybody else? Well, guess what we do next? Well, you cooled it by 5 degrees, double the cooling, cool it to 10 degrees cooler, make it 10 degrees cooler, right? So instead of stopping at 35, we'll just go from 40 to 30. And when we do that, we find that the answer doesn't double. You would think, oh, this was a delta T of 5, or 10 kilojoules. Oh, a delta T of 10 degrees C? Well, that should be around 20 kilojoules. Makes sense on a first appearance. But no, it takes almost 70, 65, 66 kilojoules. Why is it 65 and not more like 20? So in that tank, at the end, when it's 30 degrees, there'll be a little puddle of 30-degree liquid water. Not a lot of it, but just a little bit of it will be 30-degree liquid water in the bottom or the sides, however, wherever it's going to collect. There'll still be a lot of water vapor in the moist air mixture. But whenever you condense, it takes a lot of energy to condense water as well as a lot of energy to boil water. Okay, so we go back to our first law, and we would say, okay, the Q1 to 2 that needs to come out of the system, a positive heat transfer out, will be made up of the mass times U1 minus U2 for the dry air. The amount of dry air doesn't change. And really, it's going to double because the specific heat's about the same, and now the temperature change has been increased by 2. So instead of having 9.44 kilojoules to cool the air, it becomes 18.9 or 18.8 something kilojoules. It doubles. That makes sense. But I used to only have this for the vapor. I would say, well, we had the mass of vapor, and then we had the U1 minus U2 of the vapor. But when I think about it, I have to conclude something in my energy balance because some of it ends as liquid. So it's like I need to, yes?
I just want to make sure that for the dry air part,
Yes.
to get the 18.9, you do the same C sub V T1 minus T2.
Yeah. And so the C sub V really doesn't change. The mass of dry air doesn't change. It's just now 40 minus 30, so a 10 degree C change versus, yeah. Yep.
Thank you.
Yep. And so what we have to do is we have this mass U1 minus U2. If you understood this first part, great. Now we have to think about two parts for what happens with the water vapor. Some of it stays water vapor. Some of it, unfortunately or fortunately, whatever, condenses. And so what you have to do is you have to say, what is the mass that stays water vapor, even at the end, and then what is the mass that ends up in the liquid state? So for this problem, let me see if I have some numbers. Oh, I probably don't. Yes?
So how would you understand just reading the question that there is going to be liquid?
Okay. What you do is you find, one good way is to find the dew point temperature of the mixture in the beginning. And that dew point temperature is going to be greater than 30, but not greater than 35. So as I come down, 35, I'm still good, but in between 35 and 30, I hit the dew point and I start condensing.
So you need to find the original dew point temperature.
Yeah.
The basic.
That's right. Right. Which is not always easy. It's calculatable. I have a bunch of calculations here. Let's see. But I don't have the piece of paper that gives me the numbers. So, but that's how you do that. So what you do is, at the end, this is saturated air at 30 degrees C. I can now calculate how much is the water vapor in saturated air at 30 degrees C. That's what stays in the vapor. It started in the vapor, stays in the vapor. What liquefies then will be the mass that started in the vapor at state 1 minus the mass in the vapor at state 2 that I just calculated, the vapor at state 2. So I find out how much turns into liquid. Okay, this is still use of G at the initial temperature of 40 degrees C. This is use of G at the final temperature of 30 degrees C. This one is use of G at 40 degrees C, and the big kicker is this one right here. What is that one? It's how it ends at state 2. Well, it's in the liquid state, isn't it? Yes, that's it. Use of F at the 30 degrees C. And you know use of F is a whole lot lower in magnitude than use of G. So it doesn't take a large amount of liquid water that has to condense, from vapor to liquid. It doesn't take a lot of it to have a big energy impact on this. So let me just give you a summary of the calculations. This was about 18.9. To cool the vapor that stays in the vapor, about 1.02. And then to cool some of the vapor that then condenses and turns into liquid is 45.9 kilojoules. So when you add those all up, you get about 65. So this is about 70% of the heat transfer. It's not even cooling it to 35. It's really to condense it, to condense some of that liquid. And it's a minuscule, about 1.6% to cool the vapor, and then about 29% to cool the dry air. So if we go back, this is big. This is very important. It takes a lot of energy to wring the moisture out of moist air, to get it dehumidified. That's a hard problem. Ready to press on?